Alrighty folks, here's another video that's going to accompany section 6.2, your introduction to polynomials. This will be a brief discussion about end behavior and what it means on the graph. First of all, the idea of end behavior is we want to know what's happening on the far left and the far right of the graph. The in-between stuff, where usually your x-intercepts, your y-intercepts, your minimums, your maximums, all that stuff, that's not a concern for end behavior. We just want to know what's happening on the far left, the far right. So the idea is we want to know what's happening as x approaches negative infinity and what happens as x approaches positive infinity. So what I'm going to do, I think, is make a little chart here where my first column is going to be values, it's going to be the circumstances where my degree is even. And my second column is going to be the circumstances where my degree is odd. If you think about it, if we have degrees that are positive whole numbers, they're either even or they're odd. The second thing I'm going to consider is whether or not my leading coefficient is positive. Leading coefficient positive, which means a sub n is greater than 0, right? Positive. Or whether my leading coefficient is negative. So this really just gives me 4 scenarios between my degree being even, odd, my leading coefficient being positive or negative. So I'm going to make this 4-section rectangle, and I'm going to get all 4 end behavior scenarios in here. So the first thing I'll consider is my degree to be even and my leading coefficient to be positive. So my example that I'm going to think of that's the easiest one is y equals x squared. That fits the bill for what we're talking about here. Well, we know that y equals x squared goes up on both sides. So I have it going up on the left, I have it going up on the far right. I have these dots in the center here because I don't really care what's happening in the center. Right? I only care about what's happening on these sides here. And that's what I'm going to write about. So now the step that you folks have to make is being able to go from what you see here in the picture to the math statement that says exactly this picture. So here's how we write this. I want to write about the left side, and I want to write about the right side. So here's how I write about the left side. Whoa. Okay, sorry about that. My board here just freaked out on me. Okay, so here's what this is saying. As x goes to the left, well, what that means is, in math terms, we say as x goes towards negative infinity, well, what's happening? Well, the function is going up over here towards positive infinity. So we say as x goes to negative infinity, f of x goes to positive infinity. So that there is my first statement. That tells me what's happening as I go to the left. As I go to the left, this is saying left, my function's going up. That's essentially what that's saying. So the trick that you need to pull off is going exactly from that directions to this math statement here. Okay, so let's look at what's happening as we go to the right. Well, as we go to the right, the function is also going up. So I'm going to have a very similar statement that says this. As x goes to positive infinity, notice the change there that now says x going to positive infinity. That means x going to the right. As x goes to the right, my function's going up. My function's going up to positive infinity, just like it was going up to positive infinity as we went up to the left. So this whole thing is your statements for the end behavior of a polynomial function where the degree is even and the leading coefficient is is positive. So what we'll do at this point now is move on to the other scenarios, probably a little quicker. And I'm going to have very similar sketches. I'm going to write a different function that fits the bill for the other 3 rectangles that we're talking about, the other 3 areas that we're talking about. And then we'll write very similar statements to what we have here. The difference being is that a function might not be going up both times. It might be going down one of the times or down both of the times. Okay, so let's look at scenario 2. So scenario 2 says our degree is even and our leading coefficient is negative. Well, all that means, again, for an example, is we've just flipped over our parabola. Right? I mean, and again, this could be something like x to the 6th, x to the 8th, but again, the idea is on the ends, it's doing the same thing that a parabola would be doing. So this is going to be going down in both directions. Well, how do we say going down as x goes to the left? Okay, well, to say going down, so again, this says as x goes to the left, as x goes to negative infinity, not this way, our function goes down towards negative infinity. And we also need to have a similar statement that talks about what happens as our function goes to the right. So as x goes to the right towards positive infinity, our function is going also again down towards negative infinity. So when you look at these first two statements, or first two examples, they really look very similar to each other. In fact, the other two are going to look just like this. The only thing that's going to change in these is whether or not those go towards positive infinity or whether they go to negative infinity. Again, they may not go to the same infinity, but the rest of this, including those arrows, those are all looking the same, aren't they? So it's just a matter of what's happening out here. That's the only thing that's going to change. So it's kind of nice that you kind of have a mold for these problems that you can just change depending on the context. Okay, skip ahead a little too fast here. Okay, new scenario here. Our degree is odd, and my leading coefficient is positive. Well, the simple one for this is y equals x to the 1, or y equals x cubed if you prefer that function. But y equals x is going to be a really simple one that we know about, because we know that's going up to the right, down to the left, right? Okay, so we just need to be able to say this. So what's happening here? Well, as we go to the left, our function is going down. So here's how we say this. As x goes to the left, as x goes to negative infinity, f of x is going down to negative infinity. Again, remember, this is the only thing that's going to change out here, right? Whether or not that's positive or negative infinity. And then we have the right side. Well, as we go to the right, our function is going up this time. So we can say as x goes to the right, here's x going to the right, our function is going up to positive infinity. So this is how we can say the end behavior for any polynomial with odd degree and a positive leading coefficient. I'm going to clean this up a little bit. And we're going to move on to the last scenario here. So we have we're going to keep our degree odd. And this time our leading coefficient is going to be negative. So what that's going to do, again, everything's going to flip, just like it did with the even degree functions. So it's going to be going up to the left and then down to the right. So again, this is all about getting the picture first, and then writing the statement that goes along with the picture that you're seeing in your mind, or that you sketch on the paper there. So you folks take a minute. I'm going to pause this, and you folks write down what the end behavior of this function should be. Okay, so here's what I have. I have as x goes to the left, as x goes to negative infinity, it's going up. That's how we say up, towards positive infinity. And as x goes to the right, f of x is going down, and this is how we say down. We say f of x is going towards negative infinity. Okay, so this is all good in theory. Let's put some of this to the test here and do some problems here. So all we want to do with this function is state the end behavior. So I'll give you folks a big hint here on how to do this. Our leading term here, this is why we spent all this time looking at the leading term, the degree of the function. That is the only term that matters. And we'll talk about that in just a minute here, but let's at least just do this problem first. So when we look at this, we have our degree is even, and this is plus 7 out here, so our leading coefficient is positive. So you folks take a minute and write down what the end behavior should be. Okay, so remember, a picture might be helpful. So degree is even. I'm thinking parabola. Leading coefficient is positive, so it stays pointing up on both sides. And now I just need to write that as I go to the left, my function is going up towards positive infinity. And as I go to the right, my function is also going up towards positive infinity. So it's going to positive infinity both ways. As x goes to negative infinity, f of x is going to positive infinity. And likewise, as I go to the right, as x goes to positive infinity, it's also going up. Okay, so let's just take a quick look at why this is. We're going to do this very informally, but just to get a sense of why we're only looking at the leading term. When we say that x is going to infinity or negative infinity, we're talking extremely large numbers. Well, think about it. Does subtracting 10 from an extremely large number do much? Well, no, it doesn't really do a whole lot. In fact, neither does multiplying by 2, right? That doesn't do too much to the function. So it's really kind of battling out between these two terms here. And I would argue that taking a massive number and raising to the 6th power does, I know it's going to be a close call, but it's going to do a heck of a lot more than raising that extremely large number just to the 4th power. So the fact that we have an x to the 6th, it's really going to destroy all these other terms here in the long run when x goes out to infinity. Again, when we're close to smaller numbers like 10 and 100 and 0 and -5, stuff like that, the other terms are important, but in the long run here, only that leading term is going to be of any consequence to us. Okay, so let's look at one more example here, and then and that'll be the end of our exercise here. So you folks take a minute and write down the end behavior as you see it. And again, you may want to pause it because I'm about to show what the solution is here. So again, this one's a little bit of a curveball here because it's not in the normal form that we like to write this. But our leading term is not the first term in this case, but it's the only one that matters. That x to the 9th is going to pull all the weight in this problem. So this 3x to the 6th, this 7x to the 4th, this -10, really are inconsequential when we're talking end behavior here. So this is going to be an odd degree with a negative leading coefficient. So that's going to go up to the left and down to the right. And now it's just a matter of writing that out. And you should have statements that look like this. As x goes toward the left, towards negative infinity, g of x goes up, just like I drew it once before. And then as x goes to the right, as x goes to positive infinity, g of x goes down towards negative infinity. And it seems to be disappearing every time I draw it, so I'm not going to try drawing it again. But I hope this was beneficial. I hope this explains end behavior, at least somewhat. And we'll talk about this more in class when we see you guys. Take care and have a good day.